Well, hello guys and welcome back to Mr. G Physics. This is Mr. G and this time we're going to be doing a question on electromagnetism. There are a learner that asked me to please practice more questions. We'll do one or two questions today. We're going to do one. This is an easy topic. It's not a big issue. And the thing about this topic is that it's too little marks in the exam, so it's not worth to spend too much time because it's quite easy and then the marks are little. But before we move on, do not forget to subscribe for the channel so you can get the notifications and videos I post on regular basis. This question was a question 8 from the Gauteng question paper in 2023. A magnet is brought near a solenoid or coil as shown in the diagram below, and then you can see a solenoid and a magnet that is moving towards the solenoid. This instrument down here in the solenoid, this instrument here is an instrument used to measure alternated or small amounts of alternated current, so it does move on both directions in there. And the first question states the Faraday's law of electromagnetic induction. Guys, this law is a simple law, but the most important part is that it's given to you in the formulas. Here we are in the formulas. It's indirectly being given to you. This is Faraday's law. So if I were you, while my studies, I will write here Faraday's law. This one is Faraday's law. You all need to know is how to work or how to read that law. Okay, now that law says that the EMF is directly proportional to the rate of change of magnetic flux. Then we are here. Let's rewrite that specific formula for Faraday's law. EMF is equal to minus N multiplied by change in magnetic flux divided by change in time. Guys, every time, and this is not related to this topic, anytime in physics we divide by time, is going to be called rate. So make sure you make that note somewhere. Every time you divide by time, that is what we call rate. So in this part here, this is called rate of change of magnetic flux. That is called rate of change of magnetic flux. All right. So now this law says that the EMF induced is directly proportional to the rate of change of magnetic flux. Now, for you to understand what does it mean, the greater or the smaller the rate of change of magnetic flux, the faster the magnet moving, in other words, or the slower will affect the amount of EMF. And here's the law. The magnitude of the induced EMF, which is epsilon, is this letter at the front, is directly proportional to the rate of change of magnetic flux. That is quite simple, and if you look carefully and you remember, it is in the formula. They're telling you that EMF is directly proportional to the change in magnetic flux. So guys, learn from the formulas. It will help you to memorize. This one is 2 marks for the definition. Now, question 8.2. Why does the galvanometer deflect as the magnet is brought close to the coil? Well, guys, that is because the EMF is generated. That is because there is current in the solenoid. So it's quite simple. The galvanometer, what does is read small amounts of current, and that current must be a alternated current. It moves in both directions. So we have to say here, because the EMF is being generated, or you can say that current is induced into the coil. So either one is correct. The second one, if you say either one, you will get marked, but the second one is the one that I'm sure they write in the memo. But either one is correct, guys. That is the answer for question 8.2. So far, there's 4 marks. Simple. One of them is a definition, and the other one is a logical thinking question, if I may, because it is related to if a galvanometer reads current and is deflecting, it means there is current. So there's nothing to worry or stress about. Question 8.3. What rule can we use to predict the direction of the induced current? And this one is the right hand rule. And guys, you did only one rule in this topic, which is the right hand rule. That's it. So there is no more. So it's also a very easy question because there is only one rule. Now, I cannot speak about this rule at the moment because it's just a rule, it's not a law. it means rules are different. So maybe your teacher uses a rule that you understand. So we don't have to speak about the rules because everyone uses a different rule here, or some people use different rules. Give 3 ways in which the strength of the induced current can be increased. Well, once more, we have to use the formula. And let's rewrite the formula here. Write the formula every time you have an opportunity, because like that, you will remember the formula. First, everything that is here have an effect on that specific EMF there. Everything that you have there have a specific effect. When I mean, I'm not marking just rate of change of magnetic flux, I'm marking everything. I'm marking all this side. All this side here will have an effect in that specific induced EMF. Okay, so first, if you can see, if you increase N, capital N, then the induced EMF will increase as well. So what does capital N represent? We should have talked before, but I think this is a practice. You should know that one. N represents the number of coils in the solenoid. All right, so if we go here, for instance, I'm going to draw here a small solenoid, and this solenoid is going to have 1, 2, and 3 turns. This is a solenoid of 3 turns. In this case, N is equal to 3. But if I have another solenoid, and I'm going to draw now, for instance, more, there we have, here N is 1, 2, 3, 4, and 5. It's 5 turns. That is what N does represent. How many coils are turned in the solenoid? That is N. In this case is equal to 5. So N does affect E. If you have more turns in the coil, you will have a greater induced EMF. So how can we increase? One way, this one is question 8.4. One way is by increasing the number of coils in a solenoid. Second, what else we have here apart from the rate? We have the magnetic flux, just magnetic flux here on top, as you can see. How can we change that one? That one is magnetic flux. This one have to do with the strength of the magnet. So to change that one, we have to use a stronger magnet. Remember, be careful here. Stronger does not mean bigger. Okay, so we use stronger magnet. If you use a stronger magnet, the magnetic flux does increase, and therefore the EMF also increase. You can use a stronger magnet. And then finally, we're speaking about the rate, which is actually the most important one because it is the law. If you move the magnet or the solenoid faster relative to each other, the more EMF is produced. So that one is another one here. Move the magnet faster. So you can also move the magnet faster. There is more reasons you can say that to use a soft metal bar inside the solenoid. Solenoid used with another type of material, but these are the main ones that you can write here. Guys, this one is also coming from the formula. So it's 1 mark, 2, and 3. It's another 3 marks. Another very easy 3 marks. All of them are coming from the formula. In this question, many things are coming from the formula. Now, question 8.5, a coil with 200 winding turns is rotated so that the magnetic flux linkage with each winding changes from 5 times 10 to the minus 4 Weber to 1 times 10 to the minus 4 Weber in 0.2 seconds. Calculate the induced EMF in the coil. This one is a quite simple calculation. It's straightforward with not much to do here. They give you everything. When I do this type of questions, I like to write data. I don't have much space and I don't want to go to a new page that is further, but I will write the data right on top of the question. I just write in the formula. Remember, you have to write the formula. You cannot, I've seen some of my learners that like to write just the substitution. I'm working in a disadvantaged school. Some of my learners just write the substitution and then they lose marks. So here N is equal to 200. That is the first data we have. The second data we have is that the winding change or the flux changes from 5 times 10 to the minus 4 Weber to 1 times 10 to the minus 4 Weber. So the initial magnetic flux is equal to 5 times 10 to the minus 4 Weber, and the final magnetic flux is equal to 1 times 10 to the minus 4 Weber. The time is equal to 0.2 seconds. Guys, I always recommend to write the data, work organized. So now the second step here is to substitute. Now the minus, let's speak about the minus. The minus is important. EMF has direction, however, it does not belong to a vector quantity. EMF has direction, it changes direction, it's an alternated EMF here. That minus means direction, but this is not a vector quantity, this is an exception or doesn't follow certain rules that we don't speak about here. Okay, so here, minus 200. Now, also I often get the same question. The 200 must be in the middle exactly or on top. Guys, you can write it on top, so don't struggle. You can draw a line like you do in mathematics, 200, and then multiply by final minus initial. 1 times 10 to the minus 4 minus initial, which is 5 times 10 to the minus 4. There we go. I often get asked this question, the 200 must be in between the lines or on top. Must be on top. It doesn't really matter, guys. And then the time is 0.2 volts. No unit need to be substituted. Guys, that is the substitution. And there is 1 mark for the formula and 1 for the substitution. And then the answer for this calculation, oh my goodness, let's do it in the same color, is going to be 0.4. I got a positive answer. I just did the calculation here quickly with my calculator. 0.4 volts. That's what I get. And there is 1 mark for that part. Guys, this question, once more, is quite simple and is easy to get marked. However, you can see it's only 10 marks out of 150. And like Newton's law, which is like 2 questions, 3 questions, sometimes there are 3, 4 questions in a question paper. So those are topics that I like to focus more. But this is good. This is good, and it's a good topic to score marks. I hope it helped. I hope it's clear. Thank you for watching. Don't forget to subscribe for the channel, and most important, thumb up for the video that helped the video to perform well. But thanks a lot, guys. I'll see you next time. I'll see what question we'll do next time. Be my guest to ask what question do you want. I'll do it, and very soon I'm planning to do some live videos for the learners who want to join. And thank you, Mr. Jim here.